So in the last lecture, we saw the relationship of phase and the path. We talked about the optical path length. We talked about the shift in the phase by virtue of reflection. And in case of light, we realize that whenever the light is getting reflected from a denser medium, the phase will shift. But if the reflection happens from the rarer medium, the phase will not shift. It will remain unchanged. Okay. So
Yes.
this is what we saw. Also, in case of refraction, there is no phase shift. So you can say refraction or transmission will not incur any shift in the phase. Okay. All right.
Oh,
So here denser medium means the medium in which the speed of light is less is called denser. And if it is more, it is called rarer medium. So now we saw that there are different method to interfere the wave. And we saw that two methods, particularly one is called the wavefront division method. So this method is a method to create the coherent sources, right? So
yes.
unless we don't have the coherent source, it's difficult to find the, obtain the interference, which is sustainable and visible. Under the wavefront division method, we have something called YDSE, called Young's double. Slit method, we have modified YDSE. So we'll put some modification. We have Fresnel's biprism. Method. We have Lyot's single mirror method. We also have Fresnel double mirror method. Okay. Then we have some modifications. So we can see by cutting of lenses. So and there are many more. The second is called the amplitude division method. And in this amplitude division method, we'll talk about the thin film interference. We have something called air wedge. We have Newton's ring. And there are many more. Okay.
Yes.
So we'll start with the YDSE. So in YDSE, we particularly, because it's called the double slit experiment. So And then make a small cut. So cut will also have some width. So this is called slit width. And the center of the two slit, if you find the separation, from center of the one slit to center of the other slit, this is called D, and D is called slit separation. So slit width sometimes we also write as A. In YDSE, D is much bigger than A. So slit separation is going to be much bigger than A. The A will be in the wavelength range. So it will be lambda, maybe lambda or 2 lambda or 0.5 lambda. But the D will be like 10 lambda. Okay, so it's much bigger, 10 times, 100 times. So on paper, we never draw something like this. We only draw lines.
Sir, the slit is designed in such a V shape.
Yes, it means rectangular hole. So it is the cardboard actually. And then what you see is the rectangular hole actually. Okay.
Okay, sir.
And what I said is this gap is very, very small compared to the separation of the gap. So in a reality, every hole is sufficient to carry out interference, but the interference due to each hole is called diffraction by definition. So the upper hole will create a diffraction, the lower hole will create a diffraction, and it's a mathematical scenario that if we consider the slit width to be really small, then every slit will behave as single source. So this will behave as a source S1, this will behave as source S2. So we take slit as a source actually. Understood?
Yes, sir.
Now, depending on the width, the source may have same intensity and may have different intensity. So if you take equally wider hole, then indirectly you say that it will have same intensity. So these two source will have intensity I1, I2, and I1, I2 depends on width. So source intensity is proportional to source intensity is proportional to the width of slit. So you can say if we choose A1, A2 as the width value, you will get I1, I2. If A1 equals to A2, then I1 equals to I2. And because since intensity is proportional to square of amplitude, so amplitude of wave, let's write down to avoid confusion. So amplitude is proportional to width. So amplitude is square root of the width. Okay.
Okay, sir.
Now mathematically, interference is a superposition of wave which results into the redistribution of energy. The slit separation, although I'm representing like this, but it is kept very small. It is generally fraction of a millimeter. So what we call D generally it is kept a fraction of millimeter. So it can go up to few millimeters. So generally we keep as 1 millimeter or 2 millimeter max, something like that. Now for interference, the wave from the Q source must be meeting somewhere. So we need to bring a screen actually. So this is a screen. And the propagation of wave we take as towards right. So you may have some source here. Energy from the source will travel, will reach the first slit, will reach the second slit, and then after passing through the slit, will reach somewhere here. You can choose any point, random point. The center of the, two slit, the common center. We do a line from there and we call this angle as theta. So theta is called the angular position of something which we'll call later on fringe.
Okay, sir.
Now these three lines, although I have drawn distinctly, but they are very close to each other. Technically, every line is so close that the first line, the second line, and third line is like this. You can see clearly that how close are they, right? So technically, do you see difference of length?
Sir, no, sir. It's almost as if like they are coinciding.
Correct. So the angle made by each line is roughly theta,
Yes, sir.
isn't it?
Yes, sir.
Yeah. So that is why, in fact, we take or we call this angle also as theta. But the slightest distance is good enough to create the phase difference because the wavelength of light is really small. So something which is negligible for the human eye is actually huge length for the light. So in something
Oh,
negligible, we can have thousands of wavelengths, isn't it?
yes, sir.
Because the wavelength goes in angstrom. That's the smallness of the wavelength. I hope this is clear.
Yes, sir. Sir, so that's why we like differentiate. I mean, like we do not actually differentiate them in terms of angle, but then we do
Yeah,
so in terms of the length.
correct, correct, correct.
Okay, sir.
So you can draw a perpendicular from here to here. So sometimes we can extend this also. So what we technically do is we
Sir,
draw, yeah,
sir, can you just come back in like 5 to 7 minutes?
yeah, fine. Okay, so theta is the angle position of something anyway. Now, whatever wave is leaving the S1 or leaving the S2, they must reach the point P at the same time, right?
Yes,
And
sir.
to reach at the same time, traveling different distance, one must leave early than other, right? So the
Yes, sir.
one which is farther should leave the point earlier, isn't it?
Yes, sir.
So it means the two wave must have some phase difference arriving at the point P. So if I write the first wave at point P, the first wave may have the form of may have amplitude A1, and it is a traveling wave, so we can write omega t minus kx. Okay. And the second wave we can write as let's add 5 phase. So second is leading in a way, it means second has left early to reach at point P. So it is leading by some phase difference 5. Okay. Now, how to get the phase difference is a task that we have learned in the last lecture, how to calculate the phi. But right now we are assuming that phi is the total phase difference between the two waves arriving at the point P. Interference is superposition of wave, which means the resultant at point P will be the sum of these two. Okay.
Yes, sir.
Because they are interfering at a particular point x. So we can name this x value as 0. That's easy to solve. Or if you want, you can leave it as such. So we can write yr equals to So to solve these two, there are two ways. One is of course, you can use the trigonometry, but other is called the phasor. So using phasor, you can take the omega t minus kx as a reference because that is common to all.
Yes.
So the first wave will have the amplitude A1 and it is in the direction of reference. But A2 will make angle phi, right?
Yes. Sir.
So finding the resultant is pretty easy. So this is called the resultant. So this is the amplitude of resultant which makes phasor alpha. So you can write as YR equals to AR. This is how we write. Now finding AR is pretty easy. You can use the vector relation. Correct?
Yes. Sir.
So this is the formula for the resultant. Now generally we express the answer in terms of intensity. Since so AR we can write as IR by some constant. A1 is called as I1 by. So this will give you the answer. So IR is I1 plus I2 plus 2 under root I1 I2 into cos phi. The term beyond I1 plus I2, this term is called the interference term. Which means for coherent source, if two sources will arrive at a point, then the resultant intensity that we expect is I1 plus I2. What we can get either more than that or less than that, depending on the third term. So if there is no interference, then the third term will vanish automatically, will become 0. So if the source is incoherent, then third term will never appear. Because in case of incoherent source, the phase relationship will vary with time. And therefore, on an average, it will be always zero. So we can just remember this fact for incoherent source. So for incoherent source, the resultant is simply the sum of the two. This is only for coherent source. Okay.
Yes.
So so the formula becomes really easy.
Yes.
So the maximum intensity is 4 times the individual. Okay.
Okay, sir.
So let's keep it in general. So for constructive interference, also called maximum brightness, also called maxima. These all are like you can say synonyms. So for these all condition to be met, which means when the I becomes maximum, for IR max, so IR will be maximum only when this term is 1, correct?
Yes, sir.
And cos of angle is 1 when the angle is either 0 or multiple of 2 pi.
Yes, sir.
And we know this is phase difference. You can add phase differences. In general, we add 2 pi by lambda delta x. Okay.
Yes, sir.
So if you compare these two, delta x goes to lambda. Okay, so this is the condition for maximum. If the optical path difference is n times lambda, so it's containing integer one multiple of lambda. So the wave will meet in phase and will produce the maximum. Okay.
Yes, sir.
For destructive interference, one more time forward. So in this case, the IR becomes how much? So the maximum value of we can write as root I plus root I to whole square, right? So this we can
Yes.
rewrite like this.
Yes.
So where cos phi equals to -1, and cos is -1 when it is odd multiple of phi. Okay.
Yes.
So the path reference should be lambda by 2 and the odd multiple of that number. And in that case, the IR minimum will be for identical source, it will be perfectly 0. That is perfect darkness will obtain. So for non-identical source, we have dim light, but not 0. But for identical sources, it will become perfectly dark. Okay. So the region of bright and region of dark will be separated, and this separation of the two consecutive bright or two consecutive dark we call fringe width. We'll come to that. So we got the intensity relation, right?
Yes, sir.
If you remember the screen of the YDSE, The distance from the measured from the center of the screen we represent by the yn. It's the meaning of n I'll explain in a while. So every fringe on the screen we can represent in two ways, one in terms of theta, another in terms of yn. So we'll first try to find the yn. For that, we need to know certain things like this separation is called capital D. This separation we know already, it's called small d. And the rest you can express. So instead of all fringe position, we are only looking for the position of maxima and position of minima. So for position of maxima, path difference should be how much? N lambda, right?
Yes.
And to find the path difference, we can just drop a perpendicular from here because this is the simple case. And because we know this angle is theta, so this is 90 minus theta. This is S1. So here the path traveled by the light from the beginning of the source. So how we write is SS2 plus S2P minus SS1. Now luckily SS2 and SS1 are symmetrical, so this gets cancelled out. So what we are left with is S2P minus S1P. Now S2P minus S1P is basically S2Q actually. You can write it like this. And the value of S2Q you can look from the triangle it is. Do you realize this?
Yes.
Now the value of capital D, small d, and the wavelength. So if you try to find the sine theta, the theta n turns out to be very small value. So for a very small value of theta, the sine theta is as good as theta, right?
Yes.
So for very small, so we can convert the sine into tan value. So that will make it easier. So one implies and in a triangle, this using the center, the tan of theta n is how much? Isn't it?
Yes.
So that's why we write as capital Y1 by capital D is n lambda by d small d. So the position of nth maxima, this is called nth maxima. is n times lambda d by d. So if you ask first maxima, n is 1, second maxima is 2. But we also have something called zero order maximum. So we have something called order of maxima. So meaning of order of maxima, what you can say? It is the difference of number of wavelengths of two paths traversed by wave. So look at this. If you arrive at point O, what will happen? The point O,
Sir, they will reach at the same phase.
so the number of wavelengths is same in both cases.
Yes, sir.
So the difference of count is 0.
Yes, sir.
So that's why the O is called the zero order maximum.
Okay, sir.
Okay. So order means the difference of wavelength. What is fringe width? It is lambda capital D by small d. It is clear?
Yes, sir.
In case of confusion, always remember that lambda is a small quantity, so we divide by the small. So lambda by small d into capital D. Okay.
Okay, sir.
So as capital D will increase, beta will also increase, and vice versa.
Yes, sir.
But as you decrease the D, if you bring the two slits very close, beta will become too large.
Yes, sir.
In that case, they start overlapping and then they will lose the distinction which they have. So you won't be able to see the interference pattern distinctly. Rather, you will see a blur region of light. So bringing D to very small value is also not suitable for obtaining the fringe pattern. And if D is too large, then beta is very small. In that case, it is so small that you won't be able to see itself what is like a fringe. So you won't be able to see the dark region or the bright region. So extremes are always avoidable. We need to be in the some logical range which can be manifested by the brain, understood by the brain, and where we obtain the sustainable interference. It is clear?
Yes, sir.
So we obtain for the maximum, you can also obtain for the minimum using the formula. So let's do the next part. So for angular position of maxima, we have to go to the basic and we can simply remove the sign. We can erase. So we have something called angular fringe width, which means how much angle the fringe will obtain subtend on your retina. Okay.
Yes, sir.
So now you can find the position of minima. If you derive, you will get the same answer. Okay.
Okay, sir.
And similarly, you can write the okay. These are the. So generally, we are only interested in the maxima and minima position because the rest will be falling at regular intervals. So on a screen, I hope you can understand the maxima and minima, right? The fringe width.
Yes, sir.
So technically, the intensity graph will fall to zero. At the center, it will be perfectly zero. So there is a continuous fall and rise of the maxima. Okay, this is the fall and rise. And then if you shrink this diagram, okay. I'll just show you something. You have to shrink like this. Can you see it now?
Yes, sir.
It will look like this actually. Very, very
Yeah.
thin. Yeah. So in
Yes.
reality, it is very thin. So, but what I'm doing is I have just zoomed the entire thing and it looks like this.
Okay, sir.
So animation is difficult now.
Yes.
Okay, so these are the like terminology which you need to know, like zero order, first order, second order. Order means the wavelength is. What is also interesting to know that if you look at the center, there's certain thing which you need to know. So the position of the minima is called beta by 2. So on both sides of the central maxima, you will get minima, right?
Yes, sir.
At a beta by 2 distance away. And then if you move beta by 2 further, you get maxima. And then beta by 2 further, you get again minima. So if you move beta further, it will get the next minima. So beta by 2 is the first minima, second will be again beta away. 3 beta by 2. Understood? And so on.
Okay,
I
sir.
hope this is clear.
Yes, sir.
Okay. So this is the graph of intensity. This is the y-axis. So as you move above the origin on the y-axis, there is a continuous fall and rise of maxima. This continuous fall and rise of maxima and minima, this is called the interference pattern actually. In diffraction, there is not continuous rise. So in diffraction, the fall rise is drastic. So it will fall and fall and fall. So in the diffraction, the graph will vary differently. You will learn later on that graph will be something like this. I'll just show you roughly. like we keep on diminishing it on both sides. So
Okay.
that's the diffraction. In
Yes.
indifference, the variation is continuous. Okay. Now we talked about the maxima and minima, so there is something in between also, right?
Yes.
Sometimes they may give you intensity, they will ask you position. So you can see because of symmetry of the two slits with respect to S, there is no path difference from S to S1 and S to S2, right?
Yes.
Now they will give you intensity. Let's say intensity at P is half of maximum. If this is given to you, fine. So which point closest to O will have this relation? So if we use the formula, we are taking the identical source. So we can write this. So for nearest, we can take pi by how much? Oh, correct.
Yes, sir.
And this is happening when this is
5 by 4.
okay.
Yes, sir.
So how to get y? So phase difference is how much? So sin theta is lambda by 4, right? Understood?
Yes, sir.
And then we can attach tan theta. It is lambda d by 4. Something we have missed. That's why I'm saying this is dimensionally incorrect. So this will happen at 1/4 of the fringe width, right? This is like beta by 4, isn't it?
Yes, sir.
That's logical, actually. If you move beta by 2, it is complete falling. So beta by 4 is somewhere here, no?
Yes, sir.
And intensity will become 1/4 of sorry, 1/2 of the maximum, right? So that looks logical as
Yes, sir.
just okay. So question can be asked in multiple ways. One is this. After this, we have to do the modifiers. This is the basic YDSE, the very basic. And from the next lecture onwards, we'll see the variety. Like if I shift the source, what will happen? If the source is at infinity, what will happen? If we insert the thin film in front of the slit, what will happen? So we have to deal with a variety of questions. Those all are modifications. You can start solving SC Verma. That is a good book to start with.
Yes, sir.
And rest I'll cover in a lecture. So I think it will take 2 lectures for all the wavefront division method to cover. And then 2 lectures for the amplitude division method. 1 lecture for the diffraction. Okay. Assuming these lectures are short lectures, then if it is long lecture, it will take less time. So
Okay.
we'll keep more short lecture as much as possible so that we can cover it in 1 or 2 weeks or less than that.
Yes, sir.
Yeah. Then I'll start the modern physics. Then we'll go back to the 11th portion like thermodynamics and all. Okay.
Okay, sir.
Okay. Finish it as soon as possible. You can start from S or I'll share the sheet actually. Okay.
Okay, sir.